All right, today we're going to talk more about reasoning and proofs, and today we're going to prove statements about segments and angles. And we're going to use what's called a two-column proof to do it. So what's a proof? Great question. Proof is a logical argument that uses deductive reasoning to show that a statement is true. And there's several formats, but we're going to use primarily a two-column proof, and that's what we're going to use today. And we've got numbered statements and corresponding reasons that show an argument in a logical order. We got a step from A to B to C without skipping steps. So let's do an example and see what that looks like. So here the statements are already filled in for us. And we just got to figure out the reasons why we were able to use those statements. Well, first thing we have our given statement, which is a fact about what it is we're trying to prove. And then we're trying to prove this. So this should be the last statement we have. So measure of angle 1 equals the measure of angle 3. That's our given. So that's the reason we give. It was given to us. That's a fact that was presented at the beginning. So the measure of angle DBA equals the measure of angle 3 plus measure 2. Well, here's DBA. That's a little hard. Let's pick another color. Maybe gray will work better. DBA, right in here. Or let's do this. DBA is this angle here. And the measure of angle 3 and the measure of angle 2 add up to DBA. Well, that's our old friend, the angle addition postulate. So the two small angles add to the bigger angle. That works for us. And then we're going to go, let's do brown. Here this says 3, then next step it changes to 1. Well, look at this guy here, what we were originally given. Measure of 1 equals the measure of 3. So we can substitute. We can use substitution to get it to say measure of angle 1 to the measure plus the measure of angle 2. All right, so now we got to get EBC, which is this one here, this angle here, and we can see that angle 1 plus angle 2 equal EBC. Once again, our good buddy, the angle addition postulate, is helping us out. And then we've got our last statement is the measure of DBA equals the measure of EBC, which is what we're trying to prove. So that's good. And here we got DBA equals the measure of 1 plus the measure of angle 2. Here we have the measure of angle 1 plus measure equals EBC. So look at that. Our transitive property saves the day again. We started with two angles that are the same. The measure of two angles that are the same, we end up showing that two different angles are equal. Their measures are equal. And that's the type of thing we use a proof for. Let's look at another example. All right, so let's start with our given. And when I'm given more than one given, most times I like to work out what I can work out with my first given before putting the second given in. And I'm also noticing that here I'm dealing with the angle, whereas if I had the measure of angle 1, that would be the number. I know I have more tools with numbers than I do with angles, so I want to convert this from the angle to the measure because I have more work to work with then. And if angle 1 is supplementary to angle 3, that means the measure of angle 1 plus the measure of angle 3 equals 180 degrees. That is the definition of supplementary angles. And it appears I've gone as far as I can go. So let's get our second given in there. Angle 2 is supplementary to angle 3, also given. And it should come as no surprise that I'm going to convert this over to the numbers just like I did above using the definition of supplementary angles. All right. So what can we do? The measure of 1 plus the measure of 3 equals 180. The measure of angle 2 plus the measure of, well, 1 plus 3 equals 180 and 2 plus 3 equals 180. They both equal 180. So I can just use some fancy dancy substitution and plug in the measure of angle 1 plus the measure of angle 3 equals the measure of angle 2 plus the measure of angle 3. Substitution. And you can see what I mean, how easy it is to skip steps if you're not paying attention and going step by step. We don't want to do that because then it's not logical, it's not deductive reasoning, and we haven't achieved our goal. We're not proving anything. Well, we've got the measure of angle 3 on each side, and since these are numbers, we can just subtract that bad boy out. We can just use our subtraction property. But now I'm in a bind because it wants me to prove that angle 1 is congruent to angle 2, not that their measures are equal. But if I recall, when the measures of two angles are equal, the angles are congruent. That is the definition of congruent angles. So we managed to get there. We didn't skip steps. We're doing well. We're cooking with gas. And why does the order of the statements and reasons in a proof matter? Well, they have to go in a logical order. Can't be jumping around. And they have to have a reason for every statement, because that's the only way that statement is valid. But we have lots of rules, postulates, and definitions we can use. We also have one more thing. We have theorems. And a theorem is a statement that can be proven. And once we've proven a theorem, we can use it as a reason in other proofs. So theorems are our friends. We prove them once, and then we get to skip all of those steps that we use to prove the theorem as part of other proofs. So let's look. Oh, what do we have here? Properties of segment congruence. Reflexive, symmetric, transitive. Well, those are properties of equality as well. Oh, and look, they work exactly the same way. And then for angle congruence. Angle congruence, reflexive, symmetric, transitive. Same rules apply that we've used in the past without having to convert them. Well, that's going to save us a ton of time. So let's look and see which one this is. We got angle T is congruent to angle V. Angle V is congruent to angle R. So then angle T is congruent to angle R. Well, that's our transitive property. Oh, we can spell that correctly. That might help. It's our transitive property of congruence. And here we've got JL and YZ trading places. Well, that's our symmetric property. Of congruence. Now let's just go ahead and prove the symmetric property of congruence. So LM is congruent with NP. That's given. When if they're congruent, that means their lengths are the same. So there's our definition of congruence. Well, we already know the symmetric property works for real numbers, which, since we've transferred them into lengths, those are real numbers. So we can use the symmetric property of equality. Then if we have two segments whose lengths are equal, they are by definition congruent. Definition of congruence. And we are done with that one. All right, another fine example here. And this one's going to show us about switching back and forth between the segment and the length of the segment. So statement 1, M is the midpoint of AB. That's our given. So we're going to start there. So if M is the midpoint of segment AB, then we know that segment AM is congruent to segment MB. That's just the definition of our midpoint. And as we did in the previous one, AM equals MB, because that's the definition of congruence, congruent segments. Well, now we've run into a little bit of a dead end, so we gotta bring somebody else in. Well, here's AB, AM, and MB. Well, if I add AM and MB, I'm gonna get AB. Oh, wait, that's a segment addition postulate, which we talked about a few videos back. Okay, where to go from here? Well, AM equals MB. Here I have an MB, so AM plus AM equals AB, because the things I have to prove, I need in terms of AB and AM. So, oh, I forgot to write down my reason, so I'll probably miss that one on the test. That was substitution. Then if I combine my like terms, I get 2AM equals AB. This is just simplifying. And this is the first thing we have to prove. Now we just got to get to the second thing, and I need AM equals 1/2 AB. Well, I got 2AM. So if I divide through by 1/2, using my division property, I have gone ahead and proven both things they wanted to prove. So we are golden. So which begs the question, how is a theorem different from a postulate? Well, we remember from previous videos that a postulate is a rule that is accepted without proof. But as we talked about earlier, a theorem can be proven. So name that property. GH is congruent to GH. Well, if I had A was equal to A, that'd be my reflexive property of equality. So since I have a segment that is congruent to the same segment, that must be my reflexive property of congruence. Because it's looking at itself in the mirror, right? So let's move over here to the next one. If K is congruent to angle P, then angle P is congruent to angle K. Well, it's the same coming and going. That's our symmetric property. And since it's congruence and not equals, it's of congruence. Pretty simple, it fits right in. So let's go over our two-column proof again. So when we have a proof, we make one statement at a time until we reach the conclusion, wherever that may be. Because we're making statements based on facts, we're using deductive reasoning. And usually the first statement and reason pair we write, is our given. So let's look at a proof and add some more flavor around it. So our statements they're based on facts that we know are given statements or on conclusions from deductive reasoning. So, facts. Statement 1 is given. Statement 2, if angle 1 is congruent to angle 2, then the measure of angle 1 is equal to the measure of angle 2. Definition of congruent angles. That's our conclusion. So as we make a change based on a reason, we reach a new conclusion, whether we're subtracting from both sides, adding to both sides, whatever the case may be. We got to remember that the number of statements will vary depending on the proof. The reasons that we can use, well, we can use definitions, postulates, or proven theorems. That will allow us to state the corresponding statement. So they have to fit together. And remember, to give a reason for the last statement. Do those things and your proofs will come out just fine. Thanks, and we are done.